So now we begin our journey into the heart. And I know you probably have a basic understanding of how the heart works, but I want to go over some concepts and some basic anatomy to give you a better sense of how things are working here. I know we've gone over this in part when we did pulmonology in terms of blood flow to and from the lungs. But let's go ahead and get down some basic vocabulary here. We know we have four chambers, a left and right atria, and then left and right ventricles. So there's my right atrium, here's my left atrium. We have a right ventricle, we have a left ventricle. The right ventricle and the right atrium is going to be receiving venous blood from the body, coming from the superior vena cava. That's going to be delivering, blood from the head, and then and of course some of the neck areas as well. And then the inferior vena cava is going to be handling blood from the other parts of the body. But all that venous blood is heading to the right atrium. And the venous blood will go directly from the right atrium, and it will just drop down into the right ventricle. We have a check valve here called the tricuspid valve, and a generic name for any valve between the atria and the ventricle is going to be called AV valves. Okay, and that's just atrioventricular valve. But the AV valves for the right side and the left side of the heart are different, therefore they have different names. So the tricuspid valve, as the name implies, has three leaves. Again, as I said, it's a one-way check valve. We'll loop back to that point in a moment. So venous blood is just flowing into the right ventricle. And at the same time, I am having blood coming from the lungs. I know you know this, but coming from the lungs, from the pulmonary veins. And this is oxygenated blood, so this is going to be arterial blood, delivered into the left atrium, and then, of course, that's going to drop into the left ventricle. And again, it's passing through a mitral valve, and that is the other AV valve, but its specific name is mitral, because mitral is a kind of a hat that a bishop or higher ordered folks in some religious traditions will wear, like a Catholic church, a bishop will wear a mitral. It's just a two-leafed kind of hat that sits on their head. And so the mitral valve is just kind of an inverted mitral. So that's why they call it that. And again, it has two leaves. Anyway, so you're going to have the blood from the lung sitting into the left ventricle. And so now what happens is the heart is going to generate its own electrical impulse for contraction. And we probably have spoken of this before, but the heart does not need any input for contraction. It will generate its own action potentials to effect contraction of the atria and the ventricles. And we're going to go a lot into that in later lecture sections, but it is autonomous. The nervous system, such as the autonomic system, parasympathetic, sympathetic, certainly does have input into the heart, but the input is one of the nervous system modulating the beating of the heart, but the actual origin of the beat itself, which would of course utilize action potentials, starts from the heart. Again, much more on that later. But what happens is you have an electrical impulse will cause the contraction of the atria, then followed by contraction of the ventricles. And so let me tell you what doesn't happen. What doesn't happen is that all the blood from either the lungs going to the left atria or the rest of the body coming into the right atria, it doesn't just flow into the atria, then sits here and then waits for the atria to contract, and then the atria then pushes all that blood down to the ventricles. That isn't how it works at all. When the blood comes into the atria, because these valves are open, in the case the left side, the mitral valve, the right side, the tricuspid valve, blood just flows on through these one-way check valves. So by the time the atria contracts, most of the blood that has flowed through the atria is already in the ventricles. So the contraction of the atria is just to push a little bit more blood from the atria into the ventricles. So you have contraction of your atria. And then what happens is that you're going to have a following contraction of the ventricles. Now, as the ventricles contract, obviously you're reducing volume, therefore you're going to be increasing pressure. Going back to Boyle's law, we've talked about that before. So you're going to be increasing pressure as you decrease volume. Well, as I said, these AV valves are one-way check valves. So what that means is as the pressure goes up in these chambers here, it's going to slam those valves closed. So they're going to close, which means then that's going to push the blood in a different direction. So in case of the right side of the heart, the blood is going to be pushed through the pulmonary valves. And there's a pulmonary valve there. And the pulmonary valve, a three-leaf valve, is going to be pushing blood into the pulmonary artery. And the pulmonary artery, as you know, is going to be leading to the lungs. So all this venous blood is heading to the lungs for exchange of oxygen and carbon dioxide. In the meantime, we have blood again coming from the lungs where you've had your gas exchange, goes through the left atrium, goes into the left ventricle, and then when it contracts in tandem with the right ventricle, it is going to be pushed through this valve here, and this is called the aortic valve. And the aortic valve is leading to the aorta, which is this very large arch of elastic tissue, and the blood flowing into the aorta is going to be destined for the rest of the body going through the arterial system. So that's what happens there. So when the ventricles contract, both AV valves are going to slam closed, and then the pulmonary valve will be pushed open, and then the aortic valve will be pushed open, and then blood will flow through there. Now, what happens is after the contraction of the ventricles, they're going to relax, and when they relax, they're going to expand the volume, which is dropping the pressure. Well, you wouldn't want all of that work done to be pushing the blood into either the aorta or the pulmonary arteries to then flow right back into the ventricles because, again, fluid flow, gas flow, everything is driven by pressure gradient. So that means that the aortic valve and the pulmonary valve are also one-way check valves, and so when the pressure in the ventricles drop, then that means the blood will want to go back the other way, but these valves will close. That's the wrong one, over here. So these valves will close, keeping the blood in the arch of the aorta, keeping the blood in the pulmonary arteries so they can then push it downstream to wherever it is going to go. So that's kind of a review of the basic mechanics of what happens in terms of all the pressures and the contractions and such. Now let's go ahead and name some other parts of the heart and explore a few more concepts here. Since this is the left atria here, this right there is considered the left free wall. And then over here in the right ventricle, that is going to be the right free wall. And we're making a distinction between left and right free walls because what we have in the middle here is going to be a septum. And so in a sense, they're kind of a shared wall between the left and the right ventricles. Another point that we want to be aware of is that the bottom part of the heart here, we're going to call that the apex. And then I'm just going to draw, let's just go through here and just say that area of the heart there, that line area of the heart there, we're going to call that the base of the heart. So apex and base, the base is where your valves are, and the apex, of course, is at the bottom of the ventricles themselves. Now, one comment that I want to make about the left atrium, again, this is the one that is receiving blood from the lungs. You have another structure, and it's not really in the drawing, but I'm just going to just kind of go out here and say you have a left atrial appendage. And the left atrial appendage is kind of this little pocket, and you can go on Google and get better pictures of that. But it's there, and some people think that that existence of an appendage may cause clots to form. So we'll go, some think a risk factor for clots. Because anytime you have blood pooling, you run the risk of clot formation. And so there's actually a procedure there called the LAA closure. LAA closure. That's the left atrial appendage closure, where they actually go in and will suture it or close it off so you no longer have the appendage. Now, this is controversial, because whether or not the existence of the appendage actually does encourage clot formation, people argue about. So this procedure here is also controversial. Not everybody believes in its efficacy. Another idea, what's kind of cool, is that when the heart contracts, obviously things move, but when the heart contracts, the apex does not move. So apex does not move. During contraction. It stays where it is. So what happens is that the base of the heart is actually drawn towards the apex. So what you have here then is you have so it's being drawn this way. So the heart actually moves towards the apex. So the apex stays steady, and the entire base of the heart will move towards the apex during the heartbeat. Also, when the heart beats, there's a twisting motion involved. When ventricles contract. So the movement of the blood out of the ventricles is almost like you're wringing a rag. You twist to get all the water out. So the heart actually will twist like the wringing of a rag, and the base will be drawn towards the apex. The apex doesn't move, and those are some of the physical forces generating pressure in the ventricles so that it then pushes it out through either the arch of the aorta or the pulmonary valves. We're going to go a lot more in depth on that in a later lecture. Okay, I think I want to go ahead and just end this here, and then we'll pick up next time and explore another concept. So, see you till next time.